So the first condition for a binomial is that you have to have two outcomes. It has to be either a success or a failure. So that could be like one of the examples is shooting a free throw, making it, or missing it. One could be like rolling a 3 on a die. You either roll a 3 or you roll a different number. But there has to be two set outcomes that we're looking for. That way, if one outcome occurs, it will be called a success, and if another outcome occurs, it will be called a failure. There also has to be, in rule number 2, there has to be a fixed number of trials and observations. That means we have to do this a certain number of times. It has to say in the problem, roll the die 20 times, shoot the free throw 10 times. It has to tell you exactly how many times you are going to continue this scenario. The observations need to be independent. That means the probability of success on one, whether one of them happens or not, doesn't affect the next one. So, for instance, whether you roll a 3 on a die or not doesn't change the probability you'll roll a 3 on the next one. Whether you make a free throw, you still have to shoot the next free throw. It's independent of each other. So the observations have to be independent. One can't depend on the next. And then lastly, the probability of success must be the same for each trial. So again, if we talk about rolling that die, the chance of it landing on a 3 is 1 out of 6. It's not going to change. Every time you roll the die, it's going to be 1 out of 6. So again, two outcomes, success or failure, fixed number of times that you're doing it, independent observations, and the probability stays the same. If you get all 4 conditions satisfied, then it is a binomial random variable, and we're able to call it a binomial distribution. It's kind of like when we were able to call something the normal distribution or anything like that, but this is called a binomial distribution. So in a binomial distribution, we count the number of successes. So we want to find out how many successes are there in 20 attempts. What's the probability of rolling a 3 5 times out of 20? The parameters, so there's 2 things that you look at in a binomial distribution: the number of trials and the probability of success. If you notice over here on the right side, you see that big N and the mean and standard deviation. That is for a normal distribution. So for a normal distribution, we could write capital N, mean and standard deviation. For a binomial distribution, it's this B over here with N and P. The B tells the person reading it that it's binomial. The N stands for the number of trials, and the P stands for the probability of success. So we have binomial, number of trials, probability of success. So that's the symbol. And when you're counting the number of successes, it could be 0 all the way up to however many times you do something. So if you're shooting 20 free throws, you could have 0 successes all the way up to 20. An example of a binomial is a couple that's wanting to have 3 children, and they want to have all girls. The binomial setting is the B stands for binomial. The number of trials is 3 for children, and there's a 50% probability each time. So that's your probability of success. That's 0.5. Next, flipping a coin 10 times and counting the number of heads is a binomial distribution. What would be the N for that? For the binomial? In that example, what would N be? 10, because N is the number of trials. And then P would be 0.5, because that's the probability of it landing on heads. So N would be 10, and that first part. Okay, so that's what. The next scenario is the Farrells have 3 children. Their 3 children are Jennifer, Jessica, and Jacqueline. If we assume that a A couple is equally likely to have a girl or a boy, then how unusual is it for a family like the Farrells to have 3 children who are all girls? So, first of all, we have to ask ourselves the 4 things. Does this meet the requirements for a binomial setting? So the first question is, are there 2 categories? Yes. Success would be having a girl, failure is having a boy. Are there a fixed number of trials and observations? Yes, the number is 3. Are the observations independent? That means, does one affect the other? It's not, they don't affect the other, so they are independent. That means the next child, it being a boy or a girl, is the same probability regardless of what happened before. And then, is the probability of success the same? Yes, it is 0.5. So you have your n, your binomial is 3, your n is 3, and your probability is 0.5. Okay, so that shows you that it is a binomial.
How would we get the 0.5? How would we get that?
You just know that, boy, girl. So we're going to compute the different probabilities. How many outcomes are there for the first child? Well, there's 2. There's 2 outcomes for the second child, and then there's 2 outcomes for the third child. So 2 times 2 times 2, or 2 to the third power, tells us that there are 8 different outcomes. Okay, so we kind of go back to chapter 5 here. Looks like we're making our tree diagram. We have child number 1 being a boy or girl. Then we have child number 2 in each part being a boy or girl. There's 2 different scenarios there, depending on if the first child was a boy or a girl. And then we have child number 3 being a boy or girl in all 4 different scenarios. And then finally, we see the 8 different outcomes. Okay? And so I'll give you a minute to look through that. If you fill in the probabilities, you see that there's a 1/8 chance, only one, where you have 0 girls. That was the boy, boy, boy. There's a 1/8 chance of there being all girls. That is where you have girl, girl, girl. There's 3 out of 8 times where you'll have 1 girl, and 3 out of 8 times where you'll have 2 girls. So you can write those as fractions. They also write them as decimals. A lot of times in a probability distribution, you see it written as decimals. And then when you add all those decimals up, they must all add up to 1, right? So they all add up to 1, and that is our probability table. So we take some of the same things that we've learned in some of the previous chapters, and we use it here with the binomial probability. Able to find a full example. So it says a 6-sided die is rolled 3 times. Find the probability of rolling exactly 1/4. So to solve this problem, we want to, it says draw a tree diagram and use the multiplication rule to determine the probability of each outcome. So rolling a 4 is going to be our success. And if we roll anything else, so 1, 2, 3, 5, or 6, that would be a failure. And we want to find the probability of rolling no 4s, probability of rolling just 1 4, the probability of rolling 2 4s, and the probability of all 3 being 4s. So in our tree diagram, let's look at the first one. So beginning, you're either going to roll a 4 on your first roll, or you're not. N stands for just not rolling a 4. That would be 1, 2, 3, 5, 6. Then on roll 2, you're either going to roll a 4 again or not a 4. If you didn't, maybe you roll a 4 the second time or not a 4. We have not put the probabilities in yet. And then on roll 3, we are either rolling a 4 again or not a 4. So it looks very similar in this case to the one with boy girl, except the probabilities aren't 50-50. Rolling a 4 and not rolling a 4 is not 50-50. It's 1/6 chance of rolling a 4, and there's a 5/6 chance of not rolling a 4. So that's what makes this problem a little bit different, is our probabilities are different. Rolling a 4 3 times would be 1/6 times 1/6 times 1/6. So getting 3 4s in a row is actually a 1 out of 216 chance. Okay? Very, very, very unlikely. But possible, but very unlikely. Okay? And then we go through all of those. Rolling a 4 the first 2 times and then not rolling a 4. Look at that one. That's 1 6 times 1 6 times 5 6. That gives you 5 out of 216. So they're all out of 216, right? Because 6 times 6 times 6 is 216. So the most likely scenarios, if you look, are not rolling a 4 twice, have 25 out of 16, and then not rolling a 4 all 3 times is the most likely one, because there's 5 other spaces on the die, so you're always more likely to roll something else other than a 4. So that's why that one is the most likely scenario there at the bottom. It's more likely that you don't roll any 4s. But remember, we want to see in the problem, we're trying to determine the probability of each outcome, and then the probability of rolling exactly 1 4 there. So now if we add up those probabilities, we'll be able to fill in the table at the bottom. And the table at the bottom will give us the chance of rolling a Z, how many times of not rolling any 4s, of rolling 1 4, 2 4s, and then that small chance of rolling 3 4s. Now, 125 out of 216, if you're doing that on your calculator, that you should get 0.579. That was 57.9%. 75 out of 216 is 0.347, 34.7%. 15 out of 216 is 0.059 or 069, sorry, which is 15 out of 216 there. And then 1 out of 216 is 0.4%. All right, so I'm now going to, since we've done this, I now would like to, I'm going to pause. I'm going to start drawing the tree diagram at all. We could get it from the calculator. So let's look. What we would do, first of all, is we would go to second, and we would go to distribution. So second bars, and you can see what I'm pressing over here on the left side of the calculator too. So second bars, notice that's where we went for normal distributions, for like the normal CDF and stuff like that. This is also where we'll go for binomial distributions. So we're going to scroll down, and you're going to have to scroll down a little while, and way down here is binomial. There is a PDF and there is a CDF. So PDF is when you want an exact number of rolls, and CDF is if you want a cumulative, like up to 3 or up to 2. So in this case, we want a PDF because we want exactly 0 or exactly 1 or exactly 2. So we're going to hit enter here for PDF. Now, it's going to ask us how many trials. In this scenario, there are 3 trials because we are rolling the die 3 times. It's going to ask us what's the probability of success. Well, in this case, it's rolling a 4, which is 1 out of 6. And you can just type it in as 1/6. And when you hit enter, it'll change it later to whatever probability that is, which is 0.1667, whatever. 1/6 is a probability. And then as you want to fill in the table, you could say, what's the chance of getting 0, 1, 2, 3? So let's say, what's the chance of rolling no 4s? So we'll say 0 is our X value. That's how many successes we want to have, is 0. And we're going to paste that, and there is our chance of getting 0. There's 0.579. Okay. Now, if I hit second enter, it's going to come back, and let's say I want to find the probability of getting 1, 4. There that is. Second, enter, if I want to find the probability of getting 2 4s. There that is. And then second, enter, if I want to find the probability of all 3 rolls being a 4. There that is. 0.005, 0.0046. So, right there, I was able to basically fill in the table in about less than 60 seconds rather than going through and making a tree diagram and multiplying all the branches and doing all that. So in a binomial, if you want to find the exact number of successes, all you have to do is type in the number of trials that there are, the probability of success, and then how many successes you want to occur. So you might have a question on how you type that in on the calculator. That's when we want an exact number. We do the PDF, exactly 3 successes. Now, I'm going to show you one other thing. We want to find the chance of there. Let's look at this one. So notice 0 and 1 are, if we added these up, it would be about 57 and 34 would be about 91%, right, or so. So if you want to find the chance of rolling up to 1, 4, that means the probability of rolling no 4s and the probability of rolling 1 4, then you could do a binomial CDF. So I'm going to show you that. And it counts all the way up to the number that you choose. So if we go to binomial CDF, let's say we want the same 3 trials. The probability is still 1/6. Now, the X value is 1. Now, what that's going to do is it's going to count all the way up to 1. That means it's going to give us the probability of there being no successes and the probability of there being 1 success. So that should be these 2 added together when you do CDF. And you see there it is, 0.9259. So that's different than a PDF. The CDF counts all the way up to that number, whereas a PDF just gives you exactly that number. So I wanted you to see the difference there in those. But know the calculator is going to be a big help in binomial distribution. What is the probability of rolling more than 1 4? We said we added up the probability of rolling a 2 over here and rolling a 3. What is the probability of not rolling a 4 at all? That would be 0. That would be the 0.5787 or 57.87%. And then lastly, in number 6, it says use the information in the probability distribution table to create a histogram. So remember, a histogram, if there are 4 options, then you have 4 columns, 0, 1, 2, and 3, and you want their probabilities in each. So the highest it goes to is almost 0.6, so they're going up by 15% each time. So the chance of a 0 is going to be really high, right? It's really a high chance that you don't roll any 4s. Then the chance of rolling 1 4 is next, then the chance of rolling 2 4s, and then the chance of rolling 3. If we talked about this distribution, it is definitely skewed to the right, right? So it is a skewed right distribution. It has a tail to the right. So that is the binomial distribution. If they ask you to draw a histogram with it, You see how you would do that. In this, which was video 8, we're going to talk about what I was just showing you. The PDF and the CDF, they're going to go into more detail. How to do the binomial on the calculator. It's very important to be able to do these binomial probabilities using the calculator. It's going to save you a lot of time, and it's going to be a big help for the test, okay? So calculating binomial probabilities. At first, we calculated a binomial probability using a tree diagram, but that was too much work, or it's a lot of work anyway. So then we started calculating a binomial probability. There's a formula you can use. Again, that's too much work. So today we're making it even easier to calculate by using the calculator. So first, we're going to look at binomial PDF, and that's what I told you about first. You're going to use binomial PDF when you want to know the probability of getting exactly, it says, 2 hits out of 5 shots, okay? Or getting exactly 1/6 when we roll a die 3 times. So it's when you want an exact number of successes, okay? And to use binomial probability, you go to, and this is why this is in your notes, which is good. You go to second distribution, which is second vars. You go to number 0 is a quicker way to get to it, binomial PDF. You hit enter, and then you enter your parameters. And it says, in general, these are your parameters. The number of trials, the probability of success, and then how many successes that you want. That's what N, P, and X stand for here. Now, I do want to show you, I want you to write down, just because it's going to be important. This is the formula, so write down this formula. And I'll explain this formula for you. The probability that X equals K. K is going to be the number of successes. Okay, so you have how many trials there are, that's N. How many successes there are is K. The probability of success is here, and it goes to the power of however many successes you had. The probability of failure goes here, and it goes to the power of how many failures you have. And I'll show you. The formula is good to know because it could be in a multiple choice question as well, and I'll show you that in just a second. But that's the formula. N and X is the number of successes, which notice is K in that formula. Out of the board is rolling a 4 1 out of 3 times. The scenario we did earlier. We could use this formula. It would be the probability that X equals 1, because we want it to happen 1 time. The 3 stands for the number of trials. There's 3 trials. We want 1 success. The probability of success is 1/6. We want 1 success. That's why it's going to the first power. And the probability of failure is 5/6. And we want 2 failures. And that would be why it's going to the second power. So the binomial formula, it looks like a long formula. It looks tricky. It's not. It's how many trials you have, how many successes you want, probability of success to that power, probability of failure to that power. So it's really not an extremely difficult formula. It just looks like it, but our calculator will run it for us. Okay? Next one. So binomial CDF we're going to use when we want to know the probability of getting at least, so listen to this, this is going to be a tough one, at least 2 hits out of 5 shots, or getting more than 2 6s in 3 rolls of a die. We always use binomial CDF when we want to add several outcomes together. So when we want to find cumulative outcomes, more than just one. In general, binomial CDF, again, is the number of trials, the probability of success. The third part is what changes. The X is going to be the maximum number of successes. So binomial CDF always adds from the left, is what that means. That means if I want 3 or fewer successes, I'm going to put the number 3 in there because it's going to give me 0, 1, 2, and 3. Okay? If I want less than 2 successes, I'm going to put the number 1 in there because I only want 0 and 1 success. So it always adds from the left. And the number at the end of binomial CDF, that last one, is going to be the maximum number of successes. So the highest number of successes. And CDF stands for what we talked about just a minute ago, stands for cumulative distribution function. Instead of just one probability, we're going to add them up. So I'm going to show you an example of that here in just a second. So on the calculator, we're talking about a CDF, cumulative distribution function. So let's look at that. I'm going to give you an example of this. So if we want to find the probability that x is less than or equal to 1, then on our calculator, what we should do is, what we're finding is the probability that x equals 0 and the probability that x equals 1, right? Because we're finding the cumulative distribution. So if I'm saying do a CDF to 1, that's saying find the probability that there's 0 and the probability that there's 1. Because remember, that's the maximum number of successes. That means anything there or less than that would count. And so we're going to get a problem here in just a second that goes through that, okay? So CDF, again, if I said do a CDF of 1, that would be 0 plus 1. So let's move forward. I'm going to move the page here. So at the end, let's say we're talking about a gaggle of girls. So we're back to that same one, okay? Is that on there? These are it's just a practice problem. I didn't print that for you, but it's the same problem with the girls. So find the probability that a couple has 0 girls. That's easy. We go to binomial PDF. We put in 3. We put in 0.5 as our probability, and we put in 0. And we got that earlier, right? We got that probability earlier. It was 0.125. And we got the other probabilities earlier that went in our table. Now, the issue is, so we got all of those. We found all the PDF in our table. We did all those probabilities in our table. Now, here is the example here. It says, find the probability that the couple has less than 3 girls. So less than 3, a lot of people want to go put in 3 into CDF. But it says less than 3. Remember, the X value in the CDF is your maximum number of successes. So the X value, if it says find the probability that a couple has less than 3 girls, the X value is going to be 2, because you want to have 2 girls or less. So if we said find the probability that a couple has less than 3 girls, if that's the question, then we would go to our calculator, and instead of finding 0, 1, and 2, we would just scroll down until we get to binomial CDF, and we would say there are 3 girls. The probability of having 1 is 50%, and we want to find the probability of having less than 3. That means our maximum number of successes would be 2. So that's going to give me the probability of having 0 girls, 1 girl, and 2 girls all added together, and that's 0.875. So that tells me the probability of having less than 3 girls is 87.5%. What it did was add 0, 1, and 2 all together. Okay? Now, let's be real careful on CDF here. Notice number 3. Find the probability that the couple has more than 1 girl. Well, CDF only goes less than or equal to. So, but if you want to find the probability that the couple has more than 1 girl, then find the probability that the couple has 1 girl or less, and then subtract that from 1. That's the tricky part. Complementary events, right? So, to find the probability that a couple has more than 1 girl, think about it this way. You would go find the probability. So we would go do binomial CDF. I clicked it too many times. We would go find binomial CDF and say, what's the probability that the couple has up to one girl. So 0 or 1 girl. And it is 0.5, the probability that the couple has 0 girls or 1 girl. So what's the probability that the couple has more than that? It's just 1 minus that. So it's also 0.5 in this scenario. But it would be 1 minus the probability that the couple has 1 or less. That would tell you the probability that the couple has more than 1. So you could do it that way, and that's why you have that 1 minus there. Okay, and that gives you 0.5. Now, and then again, the CDF, you can make a histogram of a CDF. A CDF is calculating them cumulatively, meaning it's adding up. So 0 is just the probability of 0, but 1 is the probability of 0 and 1. 2 is the probability of 0, 1, and 2. And then 3 is the probability of 0, 1, 2, and 3. So 3 obviously should add up to 100% because that is the chance of having 0 girls, 1 girl, 2 girls, and 3 girls. So you got to be careful on, you're using a binomial PDF if you want an exact number of successes. You're using a binomial CDF if you want a maximum number of successes. And if it asks for more than, we have to do 1 minus a binomial CDF. So again, this is where it gets a little tricky, and you're going to have to pay attention on going through these. We'll have another day of this on binomial, but I'm going to give you some problems to work through today where you can use your calculator. All right, so we'll stop there for today.